All right, so now we're going to take a look at how we do sampling. And again, we have a little bit of an ontological structure here. So a tree diagram or a hierarchy chart where when we're talking about samples and statistics, and so we could even like say, hey, here's statistics, and then here's inferential statistics. And then under here, I don't know if I could right click that and choose add another one. I'm just looking add to theme. I'm not seeing it. That'd be cool if there's an easy way to do that, but I probably have to go, oh, when I click up here, do I get format options? Format options? No, I don't know. But maybe I could add another one. I'm not going to. But here under inferential statistics, we could do sampling, and then under sampling, we could do finite, and we could do infinite. And so I guess that would actually be kind of cool to see. So hold on one second. Let me see if I could figure out how to do this. So here's how I'm going to do it. I just go back to insert and I go down to the diagram and I choose hierarchy. It brings this up, and then I'm going to insert this hierarchy, and I'm going to control Z that actually, and I'll create a new slide here. And so let's do a new blank one. I'll insert that. I'm going to delete. I don't know what that is up there. That's weird. I'm going to delete that one, and I'm going to delete this one here, all that stuff, and I'm just going to copy. But did I get? I deleted something I needed. So I'm going to delete those, and it still took them. So I'm just seeing if I could delete that stuff, and then can I just delete this guy? Because when I do that, that's interesting. It takes those away. But here, if I copy this here and then put it here, and then if I drag this down, are they connected? They're not connected, but that's all right. We get the idea. I could draw a little line in there. And then I could copy this one again, and I could bring it down once more, and I could put it like right here. And then I could go up here and I could get this little line just because, and I could like just kind of like that. There we go. And I could do another line right here, and that's close enough for government work. That's kind of a funny phrase. So here we could say that this is sampling, you know, and maybe we don't have anything here yet. Nothing here yet, right? Or we could just delete that one. So maybe let's get rid of that one like that. And then here we'd have a finite population, and we would have an infinite population. Okay, and so we have statistics. It could be broken up into these two categories, and then here we could say when we're talking about sampling, we talk about infinite and finite populations, and so that's what this shows here. We could do sampling from a finite population and sampling from an infinite population. I think you're really going to like this. It's super easy. So when you sample from a finite populations are defined by lists, such as, so finite, if you go and you look up finite, finite is like the opposite of infinite. And infinite, right, the prefix in, infinite means that it's forever, limitless or endless in space, extent or size, impossible to measure or calculate, right? It's infinite. And finite means having limits or bounds. Like we as humans are finite. We've got limits, we've got bounds. And so here we're talking about finite populations. They have limits. They're not infinite. They don't go on and on. An infinite population would be like, you know, the number of items coming off of a production line, because they just keep coming. They don't stop. It just keeps coming. Like, you know, obviously, theoretically, it's not infinity. It's not going to go forever. There are limits to how much you can produce, but we don't really have an end in sight. And so that would be considered an infinite population. We'll see more examples, I imagine, when we get down to infinite populations. But a finite population is stuff that's limited. The number of people, students attending a school. Like, yeah, students could keep enrolling, but, you know, at a certain point, that's finite. So that would be like a school membership, organization membership roster, or the students who are enrolled, the list of those, that's finite. It's limited. Credit card account numbers, right? Limited. You know, theoretically, we could keep adding and adding and adding, but there's a limit to it. Inventory product numbers, simple random. So that's examples of finite populations. These aren't the best for me, actually. So let's go to, you know, let's go to ChatGPT, and we'll go into, this will be the new one. And so we'll do this here. And by the way, I've said a couple of times, I'll include a link to the ChatGPT in our course resources, and I haven't been able to technically make that work. And so I haven't included that link. So we'll just be using this in the videos. And so if you haven't seen that, that's why. So please tell me about sampling from a finite population and give me examples of populations that are finite. Finite. Boop. I love ChatGPT. Sampling from a finite population involves selecting a subset of individuals, items, or elements from a population that has a fixed number of members. Unlike an infinite population where the population size is theoretically unbounded, a finite population has a specific countable number of members. When sampling from such a population, it is essential to consider how the size of the population. I just gotta make sure I'm recording, and then I gotta turn the AC down. I'll be right back. All right, I'm back. And we're still recording. So, a finite population has a specific countable number of members. When sampling from such a population, it is essential to consider how the size of the population, capital N, so if you remember our notation, we have this notation here, and a population is, the notation for a population is capital N. And the sample size, which is sample is a lowercase n right there, relate, especially in terms of sampling with or without replacement. So are we sampling and then we put the piece back and we sample again, or we sample and we took the piece out and we don't put it back, so the next sample won't include the one we already sampled. So that's interesting, with or without replacement. Finite population, a population with a fixed countable number of members. Once a sample is drawn, the total population size decreases. So that's without replacement, right? Sampling without replacement, which can affect probabilities if sampling is done without replacement. Sampling with replacement, each member of the population can be selected more than once after each selection. So you have all these interesting things when you start to think about what is like the framework we're going to use for sampling, right? Is it going to be with, is it going to be from a finite or an infinite population? Is it going to be with or without replacement? And so with replacement means each member can be selected more than once. After each selection, the member is replaced, so the population size remains constant throughout the sampling process. Sampling without replacement, once a member of the population is selected, is not replaced and thus cannot be selected again. This is common in finite populations and means that each selection reduces the size of the remaining population. Finite population correction. When sampling without replacement from a finite population, the standard error of the estimate needs to be adjusted using the FPC to account for the reduction in the population size after each selection. So, all right, this is just like, heads up, maybe stuff we'll learn more, or maybe just like more advanced stuff that we don't get into in our book. But we'll come back to this in just a second here. In particular, we'll look up standard error. The FPC is defined as big N minus little n, big N minus 1, square root of it. Okay. Examples of finite populations. And so I'm just going to put this question here. Can you please define for me? A classroom of students, a company of employees, cars in a parking lot, voter rolls in a city, inventory items in a warehouse. Each of these cases, the population is finite, and the methods for selecting a representative sample depend on whether sampling is done with or without replacement. Finite population correction factors are used when sampling without replacement. So finite population correction, that's a FPC. That's done when sampling without replacement. Finite population correction is used when sampling without replacement to account for changes in population size during sampling. So let's see what standard error means in that context. Standard error is a statistical measure that describes the variability or precision of a sample statistic, such as the sample mean. So it describes the variability or precision of a statistic, such as a sample mean, compared to the true population, right? So let me read this again. The standard error is a statistical measure that describes the variability or precision of a sample statistic, such as the sample mean. So like, maybe we're measuring the mean, and so this is our sample's mean, and compared to the true population parameter. So compared to the population, right, how precise is the sample statistic? And it reflects how much the sample statistic is expected to fluctuate due to sampling variability. One time we did samples and everybody was 6'1". Another time we did samples and everybody was 5'8". Hold on one second. All right, I'm back. So part of what we all have to learn in life is to like deal with life's disappointments, and And emotional regulation, right? And that's all, a lot of emotional regulations in the prefrontal cortex, which is the front part of your brain. And it's not always an easy thing. Like, how do you deal with the big emotions? And so we're built to have both rational, logical thought, and we also are built to have emotional experiences. And so when we have disappointment or frustrations, how do we deal with those? And that's something we all learn throughout our entire life. How do we deal with disappointment? How do we deal with, the fact that all of it ultimately is out of our control? And we can control some stuff, but there's a lot that's out of our control. So that's part of what we're all here to learn, and what we can all help each other learn. So standard error is a statistical measure that describes the variability or precision of a sample statistic in relation to the population. So it compares the precision of the sample versus the population, how much error is there, what's the standard error. And it reflects how much sample statistic is expected to fluctuate due to sampling variability. Sometimes they're 6 foot, the mean is 6 foot from our sample. Sometimes it's sample shows the mean is 5'8". Sometimes the sample shows the mean is 5'6", right? And so we have variability. The sample statistic, the statistic we're getting from our sample fluctuates, and there's variability because of sampling, right? And it might be like, who did we get in our sample this time can change a statistic like the mean, right? The mean that shows up in our sample, and we're wanting that to reflect the true population mean, right? But and that's known as a parameter there, a population parameter, and a sample statistic. So you just can start tuning into the vocabulary that's being used here. Sample statistic is going to estimate the population parameter, but there's going to be variability in our sampling, right? So if the sample, if we're looking for the mean from our sample to make inferences about the mean of the population, the sample statistic, which is the sample mean, will make estimations, will make inferences about the population parameter, which is the population mean, and that's going to fluctuate. The sample statistic is going to fluctuate because there's variability in our sampling. So in simpler terms, it tells us how much uncertainty we should expect in our estimate of a population parameter. So the standard error tells us, like, how much confidence do we have in relation to, that our sample statistic is accurately estimating the population parameter. And so formula for standard error of the mean, and we'll come back to this probably later in the chapter as we go through the PowerPoint presentation. But the standard error of the sample mean is calculated as standard error is the standard deviation over the square root of lowercase n. Standard deviation here is, and remember, if we had a square next to it, that would be variance. So if we go back here and look at our notation, variance, right, for a sample is s squared. Variance for a population is sigma squared. And then for standard deviation, it's just s, because we took the square root of the variance. And if it's for a population, then it's just sigma, because we took the square root of the population's variance to get the standard deviation. And so this is the standard, this is the population standard deviation, and then n is the sample size. We take the square root of that, and we get the standard error here. So if the population standard deviation is unknown, the sample standard deviation s is used as an estimate. So you can see that's an S there. Hang on one second. I'm just going to go back and check in once more and see how things are going. All right, I'm back. I can only do so much. There's only so much I can do. And then I'll do my job. Smaller standard error means that the sample mean is likely to be closer to the population mean, and larger means the sample statistic, here we're saying statistic, more variability in the sample statistic, implying less precision and more uncertainty about how well the sample reflects the population. So here's an example. If you take a sample of 100 people from a population and find that the sample mean height is 170, with a standard deviation of 10 centimeters, the standard error of the mean would be, here's our 10 centimeters over, that's the standard deviation of the population. Sample mean and height. So maybe that's the sample standard deviation is 10 centimeters. And then the sample size is that. So we have that. So standard error of the mean would be 1. This means the sample mean is expected to vary by 1 centimeter from the true population mean due to sampling variability. So if it's 170, if the sample says that the mean height is 170, the population might be 170, or it might be 169, or it might be 171. So that's kind of like letting us know based upon our sample, how much does our sample truly approximate the population. Relationship to sample size. The sample size n increases, the standard error decreases. So as we increase our sample size, you'll remember when I did the thing about America and sampling people in America, at first I was like 1,000 people, and I was like, no, wait, let's just do 20. Because as you get more people, standard error decreases, and this is because larger samples tend to provide more accurate estimates of the population. Larger samples provide more accurate estimates of the population. Conversely, with a smaller sample size, standard error is larger, reflecting greater uncertainty in the estimate. If I just have a sample size of 2, I might just randomly have 2 people who are very short or 2 people who are very tall. But the more people I get, the more the sample is going to approximate the population. So that's what that means. So let's come back to our presentation here, and a simple random, and we saw some examples of finite populations. A simple random sample size of size n from a finite population of size capital N is a sample selected such that each possible sample of size n has the same probability of being selected, right? So how do you choose your sample, right? You define, like, here's my frame, these are the people I'm going to be, or these are the elements I'm going to be sampling from, and out of the population, right? Here's my frame, I'm going to sample from this frame. And you want to have your random sample, the size of it, have, that any sample you select, it's going to have the same probability of being selected. So we'll see a little bit about how to do that here in a second. So in large sampling projects, computer-generated random numbers are often used to automate the sample selection process. And so here's an example: National Baseball League, 15 teams played in the league. Suppose we want to select a simple random sample of 5 teams to conduct in-depth interviews about how they manage their minor legal franchises, how they manage their minor franchises, minor legal, that's weird. So here we would assign a random number to each of the 15 teams and select the 5 teams corresponding to the smallest random numbers. And so here are like 15 teams, and we just generate a random number, and you could do that with Excel like that. And then we get these random numbers here, and then I would copy these and paste them paste special as values, because Excel will actually recalculate if you do some stuff sometimes. So then you could sort those from smallest to largest, and you choose 1, 2, 3, 4, 5. You choose these 5 randomly as the ones that you're going to be sampling, and so that would be your sample. So that's sampling from a finite population. And it's sampling using a simple random sample, and that's the easy part. You just assign random numbers and choose the 5 smallest or the 5 largest, and so that's how you sample from a finite population. Is it's just randomly you choose those numbers and do it. So that's an introduction to sampling from a finite population.